All right, so today, November 21st, happy Friday. We talked today about a new concept called families of curves, and then we will see the surge function again. We looked at this maybe a month ago or something earlier in the term. And I just want to point out that coming up soon, let's see, Monday, we're talking about something called L'Hopital's rule, which is our last day of new material before Wednesday, which is our review day for the test, which awkwardly is the Monday when we come back after break, right? So we don't meet next week. There's no classes Thursday or Friday of next week for Thanksgiving. Our review day is Wednesday. You'll then have 5 days, and then we take the test Monday, right? I didn't intend for it to be split up like that, but that's just the way the calendar fell this semester. Questions on the calendar? Okay, and also happening on Monday is the Rainbow project is due, all right? And of course, I take projects late, but there are penalties, so you want to get them in as soon as you can, even if they're late. All right, so top of page 33, we'll begin with this daily summary. Kevin.
In this class, we use calculus to understand the behavior of the family function and we find the number of family with.
Thank you. Petri, number 1. Okay, so what we're trying to do here is use calculus to talk about general formulas as opposed to like a specific quadratic formula. We want to talk about general quadratics in this case. Ax squared plus bx plus c. You have so much comfort with that formula that you have no problem recognizing a, b, and c are just constants, right? They're general constants, but they're just constants and x is the true variable. So let's try number 2. We'll go to Andy.
Let's begin by quickly finding a parabola. F of x equals ax squared plus bx plus c that passes through the points 1, 4, and whose tangent lines at x equals -1 and x equals 5 has slopes 6 and -2.
Okay, so let's begin at the beginning. It says we want the point to pass through, we want the curve to pass through 1, 4. So what that means is that f of something is equal to something, which is the 1 and which is the 4. F of 1 equals 4, and by that, right, that's the same. But we can find f of 1 by plugging 1 into the f function. So it becomes a times what squared? 1 squared plus b times 1 plus c, which is really just a plus b plus c, yeah? So that means we have one equation here that says 4 equals a plus b plus c. And that's not enough to solve for any of those letters, but I have that relationship at the end of the day. Okay, taking a look at number 3. Oh, sorry, not number 3, but the next piece of info in this problem. We want tangent lines to have a certain slope. So what calculus thing do we need to do to think about the slope of tangent line? We gotta take derivatives. So let's take a derivative here. So f prime of x equals, and again, remember, x is the variable. Every other letter there is a constant. So what's the derivative? Do we need the product rule, for example, for ax squared? A times x squared. No, because a is a constant. So what's the derivative of ax squared? 2ax, right? I've done that before. Plus the derivative of bx, b, plus what's the derivative of c? 0. And that should look really familiar to you because we did it on that linear and quadratic approximation day, right? We started with general quadratics and then you took 1 or 2 derivatives. So 2ax plus b, you've seen before. Okay, is there anything in the problem that indicates we should go to a second derivative?
Yes.
What word would we be looking for that would say second derivative information? Slope is second derivative? Yeah. We don't. What's the word that would say do second derivatives? Concavity, right? It says something about concavity. This problem says nothing about concavity. So this is just a slope, which is just a first derivative. So we're good here. And we have the slopes at -1 and 5. And so what that means is that f prime of -1 is definitely equal to 6, right? Because it says the slope at -1 is 6. And it also means that f prime of what is equal to what? F prime of 5 is equal to f prime of 5 is equal to -2. Okay. Okay. But f prime of -1 we can find by plugging -1 into our blue formula, right? That's the f prime formula. So this becomes 2a times -1 plus the b, right? Just change the x to -1. And so this gives us a new equation that says 6 is equal to -2a plus b. And then we can do the same thing in the second equation. Here, the blue x is going to become what number? It's going to become the 5, right? F prime of 5, we just plug into blue. So 2a times 5 plus the b. So what equation do we have now? A plus b. And then those final two green equations should really look like something you can handle, right? That's a linear system of equations with two unknowns. So you could do the substitution method or the elimination method, or sometimes called the add-subtract method, right? If you subtracted those equations, what nice thing would happen? They do line up. What nice thing happens if you subtract? What happens to the b's? They cancel, right? Because you could subtract, and then you could find a, right? Subtract the equations and find a. So we're done with this problem for right now because we finished the calculus. So we'll just give you the pointers and then you can finish later on. But subtract to find an easy equation which just has a in it, and then once you know a, you can plug into either of these green equations to find b. And then how do we find c once we know a and b? We plug into this 4 equals equation. Then find c. I'm plugging into that original. Okay. So there's a little bit of algebra left to do, but the calculus is done, so we're done. Questions on the process? And what's kind of cool from my perspective is that you have the ability to create formulas that have very precise properties. Like you can make this parabola go through the point 1,4, and you can make the tangent line at -1 have exactly a slope of 6, and the tangent line at 5 have exactly a slope of -2. And if you wanted to change your mind and change those numbers, you could build a different parabola that has those properties. Okay, let's move on to 3, which is going to involve some more intense calculus and algebra. So 3, let's go to Cameron.
So B is positive for other analysis. Let's find a local extrema. Start with the breakdown.
Thank you. Okay, so first, one thing Cameron said that I want to make sure we buy is that if we just analyze this simpler version of things, and then we change the x into an x minus a, what's the impact on the graph? It's just moved over by a units, right? Right. We know that if you change an x to an x minus a, then it just shifts left or right. So we're going to analyze the simpler version and then recognize, oh, but the graph of the more complicated one is the same. It's just shifted left to right. So let's analyze that. It's complicated enough without the minus a in it. So first it says end behavior. So end behavior means we are trying to send x to what thing? Infinity. Or minus infinity, right? Could be a different number. So I'm going to copy that formula here. And let's see if we can figure out what that function is heading towards. Okay, so x going to infinity means that this x up here is really big, and then I square it, and it's even bigger. And then I divide by b, which we're assuming the whole time is a positive number. I'm just going to assume b is positive. So the whole thing up there is some big positive number, but then there's a negative sign in the front, which makes it a big negative number. And then we take e and raise it to like this big negative number. So e to the negative 100 or e to the negative 1,000,000. And both of those are very close to what nice number? It's not 1, it's 0. E to the negative 100 means 1 over e to the 100th, which is some massive, massive number, right? So this thing here in the limit actually is 0. Right? So we wrote very little, but did a lot of analysis kind of in our minds. And if you, instead of doing positive infinity, did negative infinity, would the analysis change at all? That's the very first thing we do with the x, is we square it. So that negative would disappear at the very beginning. So you can stick a plus or minus, it's the same analysis. Okay, so far so good. Now let's start doing some calculus stuff. So we'll begin with the derivative of this guy. Okay, so the first rule we need to apply is the e to the stuff rule. So what's the derivative of e to the stuff? It's e to the stuff, so we'll copy it just as it is. E to the minus x squared over b times the derivative of this stuff. All right, I'm going to do a little scratch work over here on the side, and we still have to fill in that derivative of the stuff. But negative x squared over b, in my mind, I'm just going to think of this as like negative x squared over 7, just to remind myself that b is a number, so I don't need a quotient rule. And so that's really the same as negative 1/7 times x squared, right? Just peel the x squared off of it. So what's the derivative of that? It's the negative 1/7 and then times 2x, right? So the derivative over here is just the negative 1 over b times 2x, right? That negative and the b are just part of the constant. So that's our derivative. You could put parentheses if you wanted to. I think we're okay, but certainly, are those the ones you were talking about, or did you mean the whole thing? Yeah, maybe I'll put those in just to be really clear. That's the derivative of the stuff. Okay, that was so much fun. Let's take another derivative. We have to talk about concavity anyway, so let's just do one more derivative here. What derivative rule do we need this time? This is a product rule, unfortunately, right? Because there's now another x thing in the parentheses times the x's we had to start. Now it's a product rule. Okay, f double prime of x equals. All right, so here's one thing that I like to do to try to simplify my life whenever it's possible, is that if there's a constant multiple in the whole thing, I pull that to the very front before I even consider the product rule. So that negative 1 over b and that times 2 are both constant. And so I'm not even gonna include them in my derivative. I'm just gonna put this negative 2 over b here and say, okay, I'm about to do my product rule, but it isn't gonna be affected by that constant there. So that way you don't have to keep track of them anymore. It's already in the front. You would have had to factor it out at the end anyway, so I think this makes life a little bit easier. So I guess I'll write down what I'm really saying here is that I'm thinking of this guy as being outside. And it's just an x now, right? So now we'll do the product rule in the brackets. Okay, so product rule starts first times derivative of the second. So we copy the first thing. Times, what's the derivative of the second? 1. Easy enough. What's the next symbol in the product rule? Plus second times derivative of the first. Second is just x. Derivative of e to the negative x squared over b is a problem that we've done already, right? That was your first derivative. So I think I can just copy, you know, like anything up here in blue. It's the entire answer from blue. So I'll just put this thing that's in the brackets here. Negative 2 over b, e to the minus x squared over b times x. So I'll underline that this guy right here is the entire blue, because that's the derivative of e to the minus x squared over b. Okay, and then one more bracket at the end to finish. I think we've got our second derivative there. We're going to do some analysis on that second derivative, so it seems like we want to clean it up as much as possible. And the main idea here is that you've got some stuff in the front of the parentheses, and then, in front of the plus sign. And then you got some other stuff behind the plus sign. And we're going to look to try to factor out whatever we can from both of those things that are now in color. So what do you see that's the common factor for both of those? It's e to the minus x squared over b, right? It's in both, so we're going to factor it to the front. So this equals, so I'll copy the negative 2 over b, which I had in the front anyway. And then I'm going to pull out this new guy, e to the minus x squared over b. What's left in green once we factor out the e piece? 1, then the plus sign. And there's more left in blue, but not all that much. You've got the x, you've got the negative 2 over b. You already pulled the e outside, so you just got one more x in here. So I think x squared and negative 2 over b. So how about we just change it to minus 2 over b x squared. A lot of algebra in that step. Okay, so I think that's about as good as it's going to get for the second derivative. So now let's take a step back from those calculations and start doing our analysis. Let's go back to the first derivative. Does the first derivative give you critical points or points of inflection? Critical points, right? Take that first derivative and set it equal to 0. Right, looking for maybe maxes or mins with horizontal tangents. So we'll take that guy and we'll set it equal to 0. I'll change colors here, purple. Make this equal 0. And now in that blue formula there at the end, you have three things multiplied together. There's a negative 2 over b, there's this e to the stuff, and there's the x. So technically we're setting three separate things equal to 0 and solving much easier equations. Negative 2 over b is a constant, and it ain't 0. So that part isn't going to contribute anything. Then you got this e to the complicated thing. Can e to anything ever equal 0? No. Think about the graph of e to the x. What's the horizontal asymptote? Is the x-axis, the y equals 0. Never, the e to the x graph never hits the 0 line. So even though it's complicated, that e to the stuff never contributes a solution either. So the only piece left is what value of x? Is just the x, and so x equals what number is going to give it to us? 0, right? Just make that x equal 0. There's nothing to solve. Thanks. Again, x equals 0, is it called a critical point or point of inflection? That's a critical point. So we'll name it as such. Critical point. And now we've got a little bit more analysis to do because that critical point could be a max, a flat tangent, or it could be a min with a flat tangent, or it could be neither one if it's just like an x cubed kind of thing where it flattens out but then continues on its merry way. So a couple of choices here in terms of figuring out which one it is. One thing you could do is a number line test, right? You guys remember you figure out where the derivative is positive and where it's negative and decide. And so that's one option. Another option is the thing called the second derivative test, where you plug your critical point 0 into the second derivative. If you're concave up and you're sitting at a critical point, are you at a max or a min? Think about this guy, which is concave up. It has a min. It doesn't have a max, right? And if you're concave down and you're sitting at a critical point, then you're a max, and that's what the second derivative test is. So I think the second derivative test is easier because we've already got the second derivative calculated. So let's just use it. So continuing on up here, we're going to find f double prime of 0, our critical point. And so we're plugging 0 for both of the x's in this red formula here at the end. So the negative 2 over b I'm copying. Negative 2 over b. Calculators aren't going to help us here. This becomes e to what number? E to the 0, which is? How much is e to the 0? That's a 1. And then when you change this x to a 0, and that whole back fraction disappears and the brackets becomes 1. So I'll put it as a 1 minus 0. So when all is said and done, that's negative 2 over b times 1 times 1. Negative 2 over b. Okay, what we were looking for was to know whether x equals 0 is a concave up spot or a concave down spot, which means we need to know what the sign of that thing is. Is it positive or is it negative? And it's negative because at the beginning we assumed that b was a positive number to start with. So that 2 over b is a positive thing, and then the negative in the front tells us that this guy is negative, which means that the function is concave what? Down, which means that 0 was a max. So x equals 0 is a max. Okay, we'll pause for just a moment here. There's good news and bad news in terms of doing this kind of analysis on families of functions. The bad news is it's much harder than if we had numbers in this problem, right? That b makes it much more difficult for us to do the analysis. The good news is that once you've done the harder analysis, you then have information about an infinite set of curves, right? Any number we want, as long as b is bigger than 0, we have done our analysis, and it applies to this very general thing. So it's like you work harder in the beginning, but the payoff is much bigger. Okay, questions about the x equals 0 part? Okay, so that's it. That's the only critical point. It is a maximum. Let's look at the second derivative. Again, the second derivative tells us what feature of the graph, concavity. And we're going to take this second derivative and set it equal to what number? Equal to 0. That's going to distinguish the plus second derivatives from the minus second derivatives. So I'm going to try to squeeze it in here. Equals 0. Oh, I guess I should have done that in purple. Too far back. Okay, so we're going to make this guy equal 0. Again, I see a product of 3 separate things. So again, we make each of the 3 little pieces equal to 0. Negative 2 over b is one of the pieces. Is it ever 0? It's not. B is some number, and there's no way that fraction is 0. How about e to anything? Ever 0? No. So all that's left is to solve the stuff inside the equation, inside the brackets, equals 0. And I'm not saying that's a piece of cake, but it's easy enough to do. So really what we want is 1 minus 2 over b x squared to equal 0. That's what this problem boils down to. And that right there is pretty much the reason that you guys spent all this time in like algebra and pre-calculus factoring things, is so that you could solve complicated equations equal to 0. And the reason this was easy is because we spent the time to factor it. Right? If you looked at the original red thing, this monstrous thing here, and you said, okay, make it equal 0, I don't know, I can't even begin to solve that equation. But once it's factored, it becomes a lot easier to deal with. Okay, so we're solving this equation for x. So how about we'll keep the 1 where it is and add the 2 over bx squared. So it's that. Multiply both sides by what to move the whole fraction over? So multiply by b over 2. So we get x squared equals 1 times b over 2, which is just b over 2. X equals square root of b over 2. Is that the only answer? Plus or minus, right? Because we took the square root, we need to recognize that there were two solutions. So we plus or minus. And those guys right there are candidates for being points of inflection. Right? Second derivative equal to 0. The concavity might change. Okay, so the last part of our high-level analysis involves trying to figure out what's going on with f double prime. And I'm just going to label these points kind of arbitrarily, like let's just say root b over 2 is there, and negative root b over 2 is here. 0 is in the middle, but I'm not going to put 0. All I know is that one number is positive and one is negative. And notice that I labeled my number line with f double prime because that's what we're going to be plugging these test points into. Okay, so how do we plug test points in when we don't have any concrete numbers to deal with? Well, I don't know. I mean, like we can do the middle part. What number is definitely between? 0 is definitely between these two things. Okay, so we're plugging 0 into what function? Into f double prime. We're plugging everything into f double prime on this number line. So we want f double prime of 0, which normally we would just have to plug in, but it happens that we already did it as part of our work from earlier. This is just lucky, but we did find f double prime of 0. And what kind of a number did it turn out to be? It turned out to be negative. So in here, it is negative. Okay, now it gets a little bit tougher because we don't have a specific value for b. I guess I can say that if I pick a number that's large enough, then it's going to be bigger than the square root of b over 2. So like a million, billion, trillion, zillion is what I'm envisioning. Right? Eventually, I'll find something bigger than that square root of b over 2. So we're plugging in this enormous number into f double prime, which is red. We're coming all the way to the end here, and just trying to decide if we have a positive thing or a negative thing. The negative 2 over b is just a constant. Is it positive or negative? That part is negative. E to anything is always what kind of a number? Positive, right? I don't even have to look up there. E to anything is always positive. So I've got a negative times a positive. The harder part is what's in the brackets. But we're imagining plugging in like a million, billion, zillion for that x. So this x squared is some enormous number. And then we hit it with this negative 2 over b and put a 1 in the front. So 1 minus some massive number is going to be what kind of a number? It's going to be negative. So again, this first fraction was a negative. Second guy is always positive. Last one's a negative. So the whole thing is positive. So not a lot of writing, but a lot of work goes into calculating that. And these things are not easy. I mean, like we're pushing you here. It's a big leap from the specific calculations with specific numbers to this very general family of functions idea. Okay, and then the last number we're going to pick is negative a million, billion, whatever. I think it's the same analysis. The negative 2 over b is still negative. E is still positive. What's the first thing you do with your negative million, billion is you square it, which makes it exactly the same as we had before. So over there is positive, same positive we had before. Okay, so then I think we've got our conclusion here. Anytime you're past the root b over 2, you are concave what? Up. And in between, we're concave down. And then to the left, we're concave up. Okay, so we've done our analysis. If we had another 2 minutes we wanted to spend on this, I think we could come up with a pretty accurate sketch of the graph of the original function, that complicated thing. You know where your max is, you know the concavity, you know that this guy asymptotes out at the y-axis on the left and the right. So I have a GSP thing that I've already done, which I'll pull up here. Let's see if the analysis that we came up with matches reality. So this is the graph of that function, although at the moment a is set to be 0. So that part is not there, so it's really the function we talked about. And And. There's the radical b over 2. The plus a you can ignore for the moment, but radical b over 2 and negative radical b over 2, those were the points of inflection, right? And where was the max supposed to be on the curve? Was it x equals 0? Is that where we have a max? Absolutely. When b is 1, it turns out this calculation gives about 0.7 and negative 0.7, which are these yellow dots. Does that look like the points of inflection? Seems good. Concave what out here? Concave up, in the middle, down, and then again. And what's the asymptote to the far right and far left? 0, the x-axis. So it looks great. We can, like changing a, again, is going to have what effect on the graph? Just going to shift it. So like really nothing interesting happens, which is why it was safe for us to ignore the a and just deal with the simpler case where a was 0. But let's start making b a little bit bigger. When we make b bigger, let's say I go from b equals 1 to b equals 2. What's going to happen to this number right here, that root b over 2? It's going to get larger. Is it going to get larger by as much? So you went from b equals 1 to b equals 2. So the square root of a half to the square root of 2 over 2, which is square root of 1. So this guy's going to go from 0.7 to 1, which is not as big a jump. I'm going to change b from 1 to 2. And this guy is just going to go from 0.7 to about 1, not to exactly 1. And so what happened to these points of inflection? Well, they just got a little bit bigger. They just moved a little bit farther away. Oops. But you can see that as I make b bigger, the points of inflection aren't moving as quickly as I'm moving b. Does that make sense? I'll go back to here. Like I'm going to take b and I'll drag it to the end of the screen. So like if this point of inflection were moving the same amount, it would move to the end of the screen roughly. It's about on top of each other. But because of that square root, you can see this guy really lagging behind that one, right? And maybe you've seen this curve before, this standard normal curve, which describes a lot of distributions. Like if you had 1,000 people and you measured their heights, you'd have some people that were really short and some people that were really tall, but pretty much we're all in the middle, and that's where most of the space is under this curve, right? Not a lot of people that are 7 feet tall, not a lot of people that are 4 feet tall, but we're all kind of in the middle and we clump together in this very normal looking curve. Okay, so I think that is it for that. So activity starts on the next page, and most of it is this surge function thing, but I don't know that there's time to finish all of it. So what I want you to do is jump a couple of pages to you're looking for problem 9, which is in the middle of a page. Everybody see number 9? Top of the page is 8. You're jumping to number 9, and once you finish 9, you go back to number 1 and do the surge function stuff with the graphs. Okay, raise a flag if I can help.